Hi, everyone. I'm Anka from CryptoNet Lab. So I'm a research scientist and I'm working on cryptography on SNARKs from Filecoin. So I will talk today about some recent work we did about SNARKs in Filecoin. And later on this presentation, Rosario will take over and talk about future directions in this area. So we all know that in Filecoin we have proof of storage, and the proof in this is done by this powerful tool that I will present today, the SNARKs. So to have a little bit of terminology, the miners, the storage providers in the network, are responsible of onboarding storage capacity, and they do it to earn block rewards. So they have to regularly prove that storage, and we will call them provers, as in the cryptography protocol for proof systems. On the other side, we have the nodes in the network that need to check the validity of such proofs. So to ensure that the data is being stored and maintained and secured as expected. So those are the verifiers. So we need to find a way to prove storage in an efficient way, in a scalable way. And that was done by the help of these cryptographic tools, cryptographic primitives known as zk-SNARKS. And their name comes from succinct non-interactive argument of knowledge, and the ZK in front is from zero knowledge. So what are these proof systems? They are perfectly fitted for a distributed system as Filecoin because they have a very short proof size, so they can fit in blocks in the chain. They are non-interactive, so they don't require any extra communication between the prover and the verifier of such a proof. Just publish the proof and the verifier can come and check it. They are arguments in the cryptographic sense of security, so their soundness holds with respect to malicious provers that are computationally bounded. And they are even more than that. They have this knowledge soundness property, which means that wherever a prover has to show that a statement is valid, it also shows that it knows a witness for the validity of that statement. So it knows all the process for computing something, not only the result. And we can also add an extra property that we like for privacy. So zero knowledge guarantees us that the proof itself doesn't reveal any extra information other than the validity of the statement. So a prover doesn't have to reveal extra sensitive data other than the storage it wants to, the validity of the storage. So in proof of storage, how do we do it? Any storage provider has to divide their storage capacity into this partition of 32 gigabytes that will be later on encoded in a more complicated way. I will not detail this here. And the storage is proven, this valid encoding of available storage is proved with 10 SNARKs, with 10 proofs for each 32 gigabytes. So we have to submit these SNARKs to the chain. And at some point, we will have too many SNARKs, even if they are succinct. The current block will be filled up with SNARKs. So we need to find a way to scale well those SNARKs. So it used to be that we have an onboarding limit of 40 petabytes per day of storage because of these SNARKs that were accumulating in the block. The verification of these SNARKs also takes time. So what we do when we have many SNARKs, before finding a solution for scalability, we still had a way to make the verification fast by batching it. So a verifier in the network will take a lot of proofs, a lot of SNARKs, read them, so it will be long, but merge them together in order to verify them all together at a single port. And what we are doing now with SnarkPack, we solve the scalability in the sense that instead of the verifier to read all the proofs, the prover itself can just aggregate the proofs together into a small aggregated proof, which we call SnarkPack proof, and the verifier will have only to read this small proof. So in brief, we have many, many SNARKs that don't fit in a block. And instead of putting all of them there, we will just apply SnarkPack and aggregate all these SNARK into a much smaller proof, which is logarithmic size in the number of the original initial SNARK proofs. So what are the challenges for constructing such a protocol, the SnarkPack? We use some existing work on other type of proofs, like inner pairing product proof, that allow us to commit to a vector of SNARK proofs and show that some inner pairing operation hold between those proofs, which will allow to verify validity of all of the proofs together. So each SNARK, it's made of 3 elements, A, B, and C. So we will commit to all this vector of SNARKs in 3 different commitments, which correspond to those elements. Unfortunately, this tool is very nice and can be used to aggregate SNARKs, but it has a drawback. It had a trusted setup, which in practice needs some very complicated ceremony to generate these public parameters that will later help to construct the protocol and to run the protocol. So that's not something fast and easy to organize. And we already have done it for the original SNARKs, which also have trusted setup. So we already had some trusted setup, and we will think of just reusing that. So our idea was to take the trusted setup from Filecoin and another compatible trusted setup for the same SNARKs from Zcash, and build from them a way to aggregate the SNARKs. So SnarkPack reuses those trusted setup, doesn't have to run anything new, and allows to commit to this vector of many, many SNARK proofs in a compact way, and apply these to previous works, as I said, on inner products, in order to prove that all the SNARKs were valid. So what the verifier does, it just has to read log n commitments that come from these proofs of inner product, and to do a final check that will guarantee altogether that the initial SNARKs were all valid. So we implemented the solutions. We have it in Rust. It's optimized in the Bellman framework. As I said, the public parameters are generated already from existing ceremonies from Filecoin and Zcash, and this is also this combination is also available in a code. And the benchmarks look really nice. So the proof size, compared with the batching, which grows linear in the number of proofs you have to look at as a verifier, it's really small. It's logarithmic. So more SNARKs we have to aggregate together, better proof size we achieve. Then we have the verification time, which is very nice compared to batching techniques. So we see here that verifying more proofs doesn't grow in efficiency. So we have the aggregation time also. A prover who wants to aggregate many SNARKs, for example, 2 to the 17 proofs, will do it in 2 minutes and will onboard a very small proof on chain. What to do next about this? So we have still room for some optimization, and we are working on either more theoretical version of SnarkPack, but also some implementation optimization. Also, we would like to upgrade these techniques to transparent aggregation. What I mean by transparent, there are new SNARKs out there which don't require any trusted setup. So we would like also to have a way to aggregate them without trusted setup or different techniques that don't require this. And we'll keep this SnarkPack in mind. Each time we will need to use the same kind of aggregation techniques to schemes that are similar to SNARKs, which have this structured pairing-based cryptography inside. So it's time for even more future directions in SNARKs, and I'll leave the stage to Rosario.
Hi, yes. Hi, I'm Rosario Gennaro. I'm also part of CryptoNet Lab. So Anka, can you move to the next slide? Yeah, so let me briefly say what CryptoNet is working on to continue to improve our SNARK offerings on Filecoin, and I'm going to touch on 4 specific topics: better vector commitments, recursion, SNARK-VM, and more applications. So can we go to the next slide? Okay, so let's go back to what Anka was talking about, the proof of storage. The way proof of storage works currently is that you have this 32 gigabytes that you can think of it as blocks that they're committed into a much smaller digest. When what we use for this commitment is a classic cryptographic technique called the Merkle tree. And what the SNARK basically proves, remember Anka said that a SNARK proves knowledge. What the SNARK proves is that I know enough blocks in this big digest that you can see in the commitment on chain. So one question that we're working on is, can we find better vector commitments that allow this proof of knowledge to somehow be more efficient? That means a smaller circuit, a smaller proof overhead in terms of how long it would take to produce these proofs and how computation intensive it is to produce these proofs. Next slide, please. Another question is that we would like to be able to reuse this packed proofs that Anka talked about. So one thing that Anka mentioned was that current proofs have this format. There are 3 group elements. In a cryptographic some group, there's A, B, and C, and that's a proof. There's 3 elements. And so then we have a vector of these proofs, AI, BI, and CI, and Anka showed you how we can compress them into 3 single commitments to all the proofs. And then we somehow aggregate the proofs and aggregate the way to actually prove that they're valid. The problem is that these commitments A, B, and C to the vectors are now in a different group, G prime, not the original group where the vector came from. And these packed proofs cannot be fed into another packing procedure later on. So once you pack them, it's done. So what we would like to have is a vector commitment that doesn't change from one group to another so that it could be reused. It turns out that in the most general form, this is actually impossible to achieve. So it's not like we're looking to, prove something that cannot be done, but we're trying to maybe find an efficient way to map one group into the other and one commitment into the other. That's okay, you can move ahead. So this is a more general issue, which is, can we break computation into smaller chunks and verify them independently and use the result of verified computations as input for other computations? So can we somehow prove something and use that proof as an input for something else that we want to prove? And there is lots of work in the cryptographic community about this. In particular, there are 2 systems that right now are the state of the art. One is ALO2 from Zcash, and another one is Nova from Microsoft Research. But there's more, and there's a lot of research in this idea of recursion for SNARKs. And we are trying to figure out what is the best way to use recursions in the kind of proofs that happen in this particular proof of space that happens in Filecoin. So next slide. Okay. And all of this is going to eventually come up into a SNARK virtual machine. And what do I mean by that? So what we're trying to, and this is not just Filecoin, the entire community is moving towards this direction, is that we want to remove the SNARK aspect out of the picture. We would like to be able to program code that in any programming languages, particularly like Solidity or JavaScript, smart contracts, that they would immediately compile to a verified computation. So you shouldn't be relying on cryptographic experts to build a SNARK for your computation. There should be a system where you code it and it gets compiled into something that produces a result and a proof of the correctness of that result. And of course, the biggest challenge here is to make it scalable when you have a very large program. So we have sort of, the way we're thinking about this problem, is we have sort of divided into three parts. One is the front end. What kind of language is best suited to be mapped to a VM instruction set that can be then optimized to build circuits that can be used inside of SNARK? And some of you may have seen the Lurk Metaproof talk earlier in the Orbit conference, which is something that the Crypto Compute Lab is working actively to build. Then this front end would be fed into what we call a middleware, which is exactly all these techniques to aggregate and recurse on proofs that comes from different subroutines. So if you write code that a subroutine, you would like to verify each subroutine individually and then combine this proofs of correctness into a single proof, similar to what we're doing for SnarkPack, but now for a general computation. And a big challenge, a big technical challenge comes from memory management. What I mean by memory management, you need to somehow prove that the way you change memory is correct. What you write and what you read from memory is correct. And this can be done also via efficient vector commitments. And then the back end is what is the best cryptographic proof system that is going to fit into all of this. And I think I have one more slide. Just an example of how also we're thinking ahead to other possible applications that we can bring in with SNARKs. One possible thing here, it's a very powerful tool. And let me give you an example of what we would like to build. We would like to build the ability to communicate confidentially through a secure channel through people who know something. So think of, for Filecoin, the ideal applications would be, think of IPFS, and I'm going to announce that I want to talk confidentially to the owner of a particular file. So one way, what you need is what in cryptography called witness encryption or witness key agreement, the way to encrypt messages that can be decrypted using an arbitrary secret, not necessarily a cryptographic key. And what we know is that SNARKs can somehow be used to build something like this, at least in the two-party setting, and we're trying to figure out if that can be extended to a group setting as well. And of course, with the usual issues of scalability and efficiency that come with this kind of problems. So this gives you like a very high-end, views of what the crypto net group is working on.